else on presenting the SLAM part.
Okay. All right. Yes.
Microphone is on?
Oh, yeah, let me double check the recording. It's gone. Microphone.
Is orange good?
It should be okay.
Kevin, is orange okay?
What?
Is orange okay?
I don't know, I've never seen this color.
Well, let's just assume it works because I was testing it. Okay, so hello everyone, we're group 1 and we did homework 6, which is the probabilistic localization and mapping. So this covers EKF SLAM, or the extended Kalman filter, plus SLAM. So I'm Anthony.
I'm Fardeen.
I'm Kevin.
And so today we're going to go over the 3 parts of the homework. The first part was localization with respect to a known map. So we have a bunch of markers, and when we see a marker, we are able to update the location, estimated belief of the robot's location. We have mapping with a known location. So given the robot's position, we can update the position of landmarks. And then finally, we have SLAM. So SLAM is a pretty important problem for robots because this is a problem that we all solve when we go into unfamiliar environments. We get placed into a new environment, we find the landmarks in the place, and then we're able to understand where we are in relation to the world. And we want robots to be able to do this because it's a milestone in autonomy. So we'll go over the first section, which is localization with respect to a known map. And many of you may have known this is a challenging problem because it requires calculating Jacobians and doing all sorts of crazy linear algebra. So we assume that everything is blob-shaped or oval-shaped. Assume everything is Gaussian. And we're able to incorporate information from the outside world into the robot's state through this process of Bayesian sensor fusion. So first, there are 2 parts to sensor fusion. The first part is to predict the current state, which is using the odometry model. And the second is to update using information from the world. So in this first part, we have the motion model, which is the odometry. As everyone is familiar with, we have a bunch of equations that we use to update both the state and the estimated the correlation between the state and the correlation between the state.
Within the state.
Yeah, within the state. So we have to calculate 2 values with Jacobians. So we have the motion model, and then we take, with respect to both the state and with the control signal, what the Jacobians are. And the Jacobians are a derivative or a gradient type function. So when we see a change in the motion model, then we're able to move towards a state that is consistent with our idea of the world. So this should be familiar to everyone. So we actually go through the process of calculating Jacobians, and you can do this by hand. And it's straightforward, but really the way that we approach the problem, and I think the easiest way to approach this problem is actually to...
Can you come back to that? Just in terms of notation, I don't really like the second line of the df or dx.
This one?
Yeah, because I really like to keep my cosine and sine together. I mean, it's a rotation matrix. There has to be a diagonal of cosine and a diagonal of sine. This notation is correct, and you group the values in a way which is correct. But I prefer to have, sorry, my fault. I prefer to have the.
No.
Yeah, sorry. I prefer to really see the structure of the rotation matrix. It has, so when I'm checking that, I say, okay, sine, cosine, sine. I see where they are. I find it more readable because I'm used to this rotation matrix shape. Doesn't mean it's wrong. Just when I present it, I prefer to present it keeping the two cross diagonal of cosine and sine.
So these are the Jacobians of the motion model. And we can actually solve this symbolically using SymPy. So SymPy is a really nice tool where you can do algebra in a symbolic way. So you declare everything up front. So we have an x, we have IW, we have s, and we basically write out the equations that we need. We have this f function, which returns a matrix that is the motion model, x plus r theta times the inverse of the, I forget what W stands for actually.
The wheel's position.
The wheel position plus the control, times this control signal. So we have this in Pythonic code, and then we return two functions. We return the Jacobian with respect to x and the Jacobian with respect to s, and we use this lambdify function, which allows us to pass in a matrix to the code that SymPy is generating. So we can use this code in our routines.
Just something to be careful of, the your theta, okay. In some application, your Jacobians could be expensive to compute, especially if you want to simplify it. So I would rather run that once and then reuse it.
Yeah, so in our code, we actually use the LRU cache from functools. So we memorize the function, so we only compute it once.
Okay.
And we do this in this next part in Slam 2, where we have to dynamically compute the Jacobians for different sizes of the state. So this is the observation function. This is where we're trying to find the difference between the landmark and our estimated robot position. The set of equations are also complicated. It's kind of a plug and chug situation. But we can also calculate the Jacobian for the observation function. And we can also use SymPy to do this. So this ends up being very straightforward to implement into the code. And then finally, the compass is the last part of the code. And the compass only depends on the current reading of the compass plus the robot state. And is also relatively straightforward to add into the code. I believe we didn't need to use SymPy for this.
Yeah, you don't need to because h is 001.
Right.
Yes.
So that is it for kind of the first portion of the code. We have a video of the, do I have it up here? We have a video of what this looks like for the first part. Should have opened this beforehand. I think it was this one. So when you have this implemented, you should have the robot. The robot should have an oval plus kind of this triangle. And as you move towards a landmark and it sees a landmark, it should tighten up real tight. And then when you can't see a landmark, it should the triangle should kind of expand to reflect the uncertainty in.
Did you just try throw the landmark there?
It's a wrong video. Wrong.
No. This is.
You can drive through the landmark. Yeah.
This demonstrates the behavior that I want here. So that's part one. So we can go back, and Fardeen will take the next section.
Kevin.
Oh, Kevin's in the next section.
Right. So the next section is mapping. So the idea here is to map all the markers. Yeah, you can. Okay. So the first step is to initialize the landmark. To do so, we base it on the measurement that is in the Z matrix, the current position x, and the uncertainty r, and we can compute. So here's the equation for the landmark expected position. So we take x is the position of the robot, so the vector, we only take x and y. Then z is the measurement between the robot and the landmark, and we convert it with the r minus theta. We convert it from the robot frame to the world frame.
Go ahead.
And then for the precision, no, it's previous. Yeah. Then for the precision matrix, so it's just equal to R, which is the uncertainty, because we consider that in mapping there's no uncertainty in position. And then for the update of the landmark, so it's this set of equation. Yeah. And here we have a video, and we have the video. Yeah.
Yeah,
Here's the picture of the mapping.
So it may be more interesting in the beginning.
Yeah. Also 2x speed.
Yeah.
Right. So every time it sees a landmark, it predicts the position, and then it refines it and shrinks the uncertainty of the landmark position.
So the initial position is actually fairly wrong.
Yeah, it's yeah.
And that's probably because Z is wrong, or is it your initialization which is wrong?
I'm not sure.
Because if it's given that if we have perfect localization, if you had a wrong initialization, your G function would be wrong, then it would still work. I mean, it would just put it at a crazy place, and then after observation, it would converge to the right place. If your date stage is correct, but your G function is wrong, it would still work. I don't know. Seems to be, but it could also be that just the long range measurement of the landmarks is fairly inaccurate.
Right.
Still, there's something which I find dubious. Yes.
Yeah, we had a similar problem. It was just like we were using the rotation matrix of theta instead of minus theta, something else.
We use minus theta.
We use minus theta.
Yeah.
So,
But should be plus theta for this part. For G should be a plus.
yeah, minus theta equals that.
Yeah, it's for the observations. Your H function should have minus theta.
Okay, well, that's
But in your initialization function, you should have a plus theta.
Maybe quickly look at how we did that. This is the mapping base, right?
Yeah.
Mapping base.
First line of the code. It's there.
Oh, minus theta.
Yep.
Yep.
That would explain that would explain the kind of weird initialization you have, and that might, if you copy pasted this stuff in the initialization of the SLAM, it might explain some issues you had as well. If you had some issues, I don't know.
No, Slam seemed to be working okay. This is not what I want. All right, so
okay, the next part is
So just to as a kind of feedback on that, because we have perfect localization, and we have a nearly quite well-behaved observation function for mapping. You can see that even with bad initialization, it converges to the right place because the localization is perfect. So you still see the thing at the right place. So it's a good example of the convergence process. But it's also a good example to see that if you put that at the wrong place, even with an uncertainty which is not representative of reality, the filter is going to just converge. So the uncertainty that the filter gives you is not how uncertain you are, but it's not the precision. Some people, beginners, I did that, believe that the uncertainty you report with a Kalman filter is the precision of the system, and it's just a confidence of the system in itself, not the precision. So if you want to measure precision, you have to compare with the ground truth. Okay, that's something important. So the uncertainty here is just how much the system believes in itself, and you can see that even with crazy initialization, it still believes very much about it at the beginning. Yes, keep going.
all right, so Fardeen.
okay. For SLAM, Anthony over here did a pretty good job of selling SLAM and why it's important, but essentially it's you're recording both the position of the robot and you're mapping the landmarks, unique landmarks at the same time. And so how does it work exactly? There's two pieces of information that are something to pay attention to. So the first one is the state. So the state actually dynamically changes as you see new landmarks, and then it also updates as you see landmarks that you've already seen. And then second, the Jacobian of the motion model is also a bit different because it is dynamically calculated for a given landmark, and of course the robot. And then, so how did we calculate that Jacobian dynamically? Again, we used SymPy. So SymPy, and we have a video showing this, but SymPy basically uses a given landmark to dynamically calculate the Jacobian of your motion model. And we have a video which shows how to use it pretty well. So yeah, you can see, so if you've measured like 5 landmarks and you give an ID, or never mind, you might have to pause it.
Yeah, it's like
It's too fast, yeah. It's at double speed. Okay. Just pause it. Okay. So if you have observed 3 landmarks and you're trying to calculate the Jacobian for landmark 1, you can see that the first 3 columns are for the Jacobian of the motion of the robot, and then the first set is going to be the Jacobian for landmark 1. And then if you were to change it, so play it, keep playing for the next iteration.
This one's nice. You see the bunch of zeros.
Yeah, and so yeah, exactly. So yes, if you've seen 5 landmarks, then the number of zeros will go up in proportion to that. And then as you change the ID, I showed that at the beginning of the video, I think. Or maybe I didn't, but yeah,
you did.
Yeah, if you change the ID, then the Jacobian will change with it. So that's like the beauty of SymPy. And then, so that's it for that. And then, yeah, you can see like a picture of our SLAM in action. So that's the hallway that you're seeing with all the landmarks mapped. So you can make out like that L shape, and yeah, that's it.
Yeah. Well, why don't we actually do a SLAM demo?
Yeah, let's see it in action.
Who wants to drive?
Kevin.
Sure.
Test engineer. Flight test engineer.
Hopefully the turtlebot's still alive.
I can it's there.
Okay, so we're in the hallway, down by the professor's office, and there's a bunch of Aruko tags that are set up along both edges of the wall. So as we're navigating down the hallway, the code is seeing the landmarks. This is exactly like Probablistic, just in the real world. So we can see, every time we see a new landmark, the map gets updated, the position of the landmarks and their uncertainties.
I mean, some of the uncertainty may come from calibration problems, some of the Aruko detection. There's some stuff that looks a little bit off, but I don't think that's your fault. I think it's the field of view of the camera is really limited, and that makes for a not very well conditioned problem. And I feel that the IMU is also doing something weird on the robot. So I had troubles as well to get something which was really clean. This is actually super clean, but when I turn around, I tend to lose some of it.
Yeah, we had the same issue.
Yeah. When we turn around and we go back, there's this one landmark that's seen kind of out of position, and so when we see the landmarks again,
if it's a mirror reflection.
Yeah, I think it's the door. I think there's like one of the doors is like reflective, and so like because we had that wrong observation in the beginning, our positions of the other landmarks start to change, and it looks a little less clean at this point. But you can kind of see how the map kind of changes as we see and re-see landmarks.
Yeah. Actually, what you're seeing also is a correlation effect between the landmark, which means that when you see some of them, it moves all the map, even though you see only a few of them. And well, you should see the correlation matrix as a kind of way to get the data to flow between landmarks. Actually, it was one of the better maps I've ever seen so far. I didn't manage to get one, so you're a good driver. I think it depends on the driver.
It's probably the driver, more than the code.
So this is it for our presentation.
What you could also see with this type of thing, which would be interesting, I haven't implemented it, is once you have a map where you kind of believe it's good enough, freeze it. So have a flag, say, okay, don't want to update the map anymore. And now I just want to do localization. And then if there's an error, it's going to move only the robot instead of moving the map and the robot to get the right solution. That's fairly good representation. It was hard, I couldn't get very excellent map, which I think is due to the low field of view of the camera. I think if we had a larger, like a 360 sensor, we could get something. So at the next update, we need to actually get on the Thunderboxes to buy RP LiDARs. They're cheap, and that would make it a bit better in terms of mapping. Also, they have longer range because the Kinect is quite limited.
All right, thank you, everyone.
Thank you.